on Wednesday, and that one is plotting things in 3D. In particular, this is the function we want to plot. And as I mentioned already, computers are very good at repeating certain tasks, but they have to be told precisely what to do. So they're stupid in a way, okay? They're still just machines. However, they can be pretty mighty when properly programmed to do something. So if I wanted to, like if you're seeing, you see me, right? You have eyes and like, you know, you have a brain that interprets what your hardware, meaning eyes, are seeing, right? So there's software, there's hardware, it's all working together, and you're seeing me, but what are you actually seeing? Do you see anything here? On my back? Do you know what I have on my back? Do I have anything printed on my shirt on the back? You don't know, right? So what you're seeing is a projection. You already have software that figures out, but you don't see through me, right? Your vision is not X-ray vision. Right? So you don't see through me, so you see certain impression of me, right? So now if I want a computer screen to do the same, okay? If I want to plot in 3D, I have to figure out that projection. What projection am I going to plot? This one, this one, this one, this one. I have as many projections as you might want, right? Not to mention if you start slicing me up in X-ray vision, right? So we need to tell computer precisely what to see. And regardless of how that is done, but that's why I want to tell you the difference between sort of like 2D plots and 3D plots, because in three-dimensional objects you have to figure out projections. Okay? And lighting and how things work in 3 dimensions, as opposed to just plot, you know, X points of a circle, right? That are right in front of you. When you're plotting a circle in 2 dimensions, all the points are right in front of you. You just decide on what color of the line would you like. That's way easier than figuring out which projection to plot in 3D. But regardless, we start with points. So we realize, okay, for a 3-dimensional surface, this object, okay, I have to figure out where are the points. And I have surface. So I have in x, y, I got to parameterize this surface and give it points, and typically on a regular grid. So we have to figure out points in x and y to actually calculate the surface as a z portion of it, and then give computer x, y's, and z's to plot. Then computer can actually, these days, easily add color to it and whatnot to make it look pretty. But at the essence of it is points on that surface, so it can actually figure out what to do. So what we really do give to computer, and that's good what this surface plot is going to do, is we give it these points, we figure out how to, what is the grid in x and y that we're going to give it. And since it's an x and y, we also have to figure out how to give it to the computer. So x's we're going to give in one matrix, and matching y's, we're going to give it another matrix. Because I can calculate z's using those matrices x and y's in corresponding locations. Yes? So that's what we went through last time. Basically, I will have matrix of x's, matrix of y's, and then we're going to calculate z's in all of the corresponding locations. Using whatever, in this case, we're going to actually have a function. It might be also just measured data that comes from somewhere else. And then I'm going to plot those x, y's, and z's. But I have to have sort of a grid of x's, a grid of y's in 2 dimensions, and then corresponding z's. And then computer will actually do the rest, this projection and what it is that you want the computer to plot. Okay? So we started doing that process, and there are some built-in functions, and I'm going to go to my Jupyter. So the assignment was to create xy coordinates in -5, 5, -5, 5. So both my x's and y's are in -5, 5 range. To get a nice set of points in some range, I typically use linspace. So I give starting point, ending point, and how many. So this is called discretization. And now I have x's, but those x's and y's are just one-dimensional arrays. I want a grid of points that kind of have to cross each other. Right? And this mesh grid will actually give me that. Okay? So when I execute what we started last time, okay, let's just print x's and y's. Okay. I'm gonna do less points just to see visually what is being done, and then I'm gonna, okay. So basically, x's are from -5 to 5, and there's 5 of them. And this matrix X is just this row kind of repeated 5 times, because it's for however many Y's I have, and I have 5 of Y's. So just repeating these X's. And then my Y's are also repeated by column Y's. And when I kind of cross them, I get all of the combinations of these points in a plane. So for every location, so there's a location here, I have in the middle. So 0, 0 falls in the middle of this range, right? So there's a corresponding location here in X and corresponding in Y that describes a point 0, 0. And if I now go compute z's using some formula, in the same location of z, I will find what is z of x, y. Yes? So again, this mesh grid is just a way, a template to get these points in the plane. Great. So I have already thrown in a function 2 minus x squared. Remember, this is exponential. So x squared, y squared, could be any number, I chose squares. So now let's plot those, okay? The very basic mechanics of plotting, so this is just really getting the points. Now I have x's, y's, and z's. And there are 3 matrices just like this. So when I grab a location, for instance, here in the first row and the second column, this location in x gives me the x coordinate, y coordinate, and z coordinate, okay? And an entire set gives me, describes this surface on a grid in x and y. So let's plot it. Technically, all I need to do is plot x, y, and z, x, y, z, and hope that it figures it out. However, we need a new toolkit because 3D works in terms of projections. I have to have a special module that does that. Okay? Because again, with 3D points, you have to pick projections and whatnot, and that's a little more involved than just XY graphs. So because of that, we're going to import another module. So I have imported NumPy as MP. We're still going to work with the regular plots. So now it's actually plotting part. I'm going to still import my friend matplotlib.pyplot as PLT, because essential frame that I'm going to see on the screen is the same as in any figure. But it's what I put in that frame, the projection that I put in that frame, that's handled with so-called mplot3d. So we're just going to say from MPL toolkits mplot3d import axis 3D. And it's this line that you're just going to learn and have on your, once the exam is about to come, you're going to have a little cheat sheet. Okay? And this is something you can definitely put on your cheat sheet. But basically, again, I need to figure out in this frame that I'm going to see how to handle these projections of 3D objects, and this is the toolkit that does that. And I have to inform Python that a 3D projection is coming. And this is how we're going to do that. For that, I have to basically start a little more essential. Before that, when I did plt.plot, it would just plot something. So there are certain defaults that just go in and plot for me, okay? Now I have to kind of step back and do things a little bit step by step. So first I'm going to give myself a figure. Figure is basically what we see, the entirety of what we see. It's an object that fits in everything else that I want to fit in there. So I'm going to say plt.figure is basically what just creates figure. Actually, if you just execute it, not much will happen because I didn't put much in it, but it tells me, hey, there's some figure going on there. But since I want to modify that object potentially later, I'm just going to grab, this is called a handle from it, and call it fig. So we kind of have to do step by step simply because I want to modify it later. Then I'm going to this figure, I'm going to add a subplot. And there will be in this figure only one plot. And these subplots, the way they work, we typically have number of subplots, columns and rows, and then which one that I'm referring to. Since there will be only one, then it's like one by one, and subplot 1. And annoyingly, add subplot doesn't work with commas, but you have to just put 1, 1, 1. And it's annoyingly because plt.subplot is in one module and this one in a slightly different one, and they have slightly different formatting. And this is where we're going to tell it, hey, projection is the 3D one. So because I wanted to modify my figure to be a 3D projection, I had to go through this create figure object first, and then in the next step tell it it's going to come as 3D. Because it requires this processing. This is where since this is now axis that will be 3D axis, and since I want to modify them further, I have to grab that handle from Python, otherwise I can just let it go. But in this case, when I want to modify something, I gotta grab the object. So this axe is grabbing, it's storing the information. And then I can basically just say plot surface is the function that I need. And technically XYZ will do the trick. And somehow I always have to do things twice. Part of it because it's digesting. Okay. So it picked certain defaults for me, and it gave me a projection of the surface. It doesn't appear to look like similar to what I had on the slides, right? So first things first, let's smooth it out a little. So now I'm not going to plot only 5 points. Let's give it at least 20. Ah, that's prettier. That's blue is a choice by default, right? We can play with color maps. And one way to do that is CMap. And the colorful sort of rainbow is a jet. There's just the name of the color scheme. So if you do CMap equals to jet, okay, now I look similar to what I kind of wanted or had in my slides as an objective. Mm-hmm. So the first 2 lines is essentially telling it what to use, which modules. The first one is our standard plot graphs module. Okay, any graph you see or any figure is going to be really this module. this one is saying, okay, this one handles these 3D projections because three-dimensional objects are a little more complicated. In 2D, I see everything. In 3D, I gotta pick a projection. And now, because I'm telling it specifically, this is a 3D projection is coming because it has to know how to handle it and how to create axes for this thing. It's not 2D axis, it's three-dimensional axis, right? So because of that, this is the projection equals to 3D when I'm telling it, I have to actually first to create the figure and then modify that part. Because otherwise, the default is 2D. Okay? And these are the steps. And actual functions that plots things in 3D is plot surface x, y, z. And I can now, defaults are picked for me. I can change colors. I can still do labels. And yes?
I was just going to ask, what do the three numbers mean whenever you do a subplot?
This 111, number of columns, number of rows, number of columns of these subplots. It's an arrangement of subplots. Let's say that you have 2 by 2, you would have 2, 2. And then when you say 1, it's like whatever else is coming, it's in that first plot, right? Because you could have multiple. So you will have that in homework that is coming, you will have subplots. And there's that PLT subplot works similarly. It will, in that one, you would just put 1, comma 1, comma 1. But it's the same thing. Number of columns, number of rows, number of columns, and then index of the plot you're modifying. Okay? And as I said, annoyingly, PLT.subplot would require 1, comma 1, comma. It requires commas, and this one doesn't, and I didn't create it, so I gotta work with it. And then plot surface. And again, it picked a projection, and you could play with that. Okay? There's different others. I'm not going to go into much detail. I just want you to know that whenever you have a picture, you can always, whatever it is that you see, from colors to lines to labels, you can modify. And you can find out how. And I'm listing here this module and plot. Plot surface is the one that I showed. You can quickly replace it with plot underscore wireframe and see what it does. There's contours. Contours are projections. You can create a field of arrows if in transport phenomena you want to plot a velocity field in future. You would use function quiver, so forth. And you can place, so this is an example of a wireframe, okay? This is a contour in 3D, and this would be a projection contour which is available in PyPlot, okay? All for the similar functions here, plot. So it depends what you want to visualize, so it's motivated by what it is that you want to visualize. And you can have fun with color maps. So I told you jet. Now change that jet to a choice of a color map here. This is the range of colors. So you can try copper, you can try cool, you can try spring. Give it a shot. And this is really just a sub-selection that fits on my slide. There's way more than that. You can go to this link and look at others. Right. This is the part where I'm going to pass around cookies. So the reason why we're given cookies today, starting here, important in my research. So, I am by training applied mathematician, and the nature of applied math is that you gotta apply it to something. Okay? And it was fluid dynamics that was always interesting to me, like things moving around, and moving around in a very complex and nonlinear way. That nonlinear, so everybody has done some differential equation, right? So there is a differential equation, not only a differential equation, but a partial differential equation, meaning that we're not in one dimension, but in multiple dimensions. That is relating velocity of a fluid and the pressure of a fluid in a very complex way. It's called Navier-Stokes equation, and you're going to get introduced to that equation in transport phenomena. It's really guiding how fluids flow, any type of fluids. It could be ocean, okay? Or it could be a river, or it could be your local pool, neighborhood pool, or it could be fluids, oil, gas, in subsurface. Okay? And water, of course, water is always around. Now, what's really changing in all of these various ways is the condition, both from the range of velocities we're looking at and range of pressures to the sizes of the spaces we're moving through. So in a regular rock, well, we have cookies. Cookies are porous media, just like rocks are, just a little yummier. So you will have friends geologists, and they always lick rocks, by the way. So, you know, cookies are better in that sense. So there is, if I poured water on this, water would go in, right? It'll make cookie also very soggy, so there are certain mechanical properties that change as I add water, right? And we in subsurface study that. And I actually study and simulate fluids moving through these pore spaces. So I kind of zoom in and move them. So I'm going to show you some visualization of how that looks like. Okay. So here is a complex fracture. This fracture, there's a tight gas sandstone up and down, and I see some very pretty crystals. Quartz. It's really pretty. If you ever went to a museum and there's like geode, those are the quartz crystals. They're colored by whatever impurity was flowing through. Okay? They can have pretty colors. But this is quartz, and most of our reservoirs, well, the reservoirs we like, are 90% quartz and above. That's referred to as the quality of a reservoir. Those have very good porosity. We know how to describe them. We know how fluids move. We can recover from those easily. The moment they have lots of clays and feldspars and lithic fragments and whatnot, that's when we get into a mess. Okay? Now, in this case, I actually had a fracture, and that fractured fluids are passing by. They're going to leave whatever is in the fluid, whatever is in that brine. And that has created crystal growth that is actually bridging fracture open. And in this particular reservoir, it's important. These are small. See, this is 500 micron. Okay? So aperture of this fracture is really small. What you see up there is really 0.5 millimeter. Okay? But it's the main pathway in this reservoir. And this is actually how the pore space is between. You're looking at a plot surface, just in a different software. Okay? That is basically plotting the surface in between you can shoot sharp lines, that's where the crystals are. Okay? And your fluid is moving through. I can plot things in different ways, so I can also plot, well, how much space do I have for every xy point? That's aperture field. Okay? So you can see where it's blue, this is my color bar, and it goes from 0, okay, 0, nothing, to up to 1 millimeter or so. Okay? And it's very different. And this is where I trap fluids as they move through, because when I have two fluids competing on the pore scale, they're going to trap. So I'm going to actually play a movie for you. Movie time. No popcorn, sorry. Popcorn wasn't offered. So movies are the frames, just like whatever figure you produce today. You could put a a sequence of those figures together and zoom them by our eyes really fast. That's what movies are. They have frames per second. They play, for instance, 20 frames per second, and you think it's a continuous movement. No, it's discrete. We know that by now, of course, right? It's just really 20 frames played really fast. So I'm going to do that, and it's going to appear as if this non-bending fluid, like oil or gas, is moving into my, this is a model fracture. It's moving through. Okay? And you will see, so this is what contouring, there's a contour F, or variant of a contour command that I have briefly introduced, that is going to plot the contour of this oil coming in and fill it with red color. So it's a visualization choice, that's all it is. Okay? But from this movie, it'll appear that this fluid is really moving. And because I was solving a relevant equation underneath, right, it appears that it's real. It is a result of a simulation. So this is the importance of visualization. Without it, I can't actually completely evaluate whether what I got is right, whether my prediction is right. Okay? This is a small example, again, on a small scale. And these tight spots are sort of holding up the fluid. And when I go back differently, and this is what drives us nuts in porous media. You never go in the way you go. You never go out the way you go in. And in the process, you could trap fluids too. So it takes a moment to withdraw and reduce capillary pressure to actually get out. And this process is drainage. Have you heard of drainage? If not, you will hear a lot about it in petrophysics. Okay? So when my non-bending fluid that preferentially doesn't want to be in the reservoir, actually, the other one that is here white wants to, so that's typically water and sandstone. When non-bending fluid is displacing bedding, I have to push in, and then if I want to withdraw, I kind of reduce that capillary pressure, but it takes a moment and I don't go way back the same way I went in. And often in the process, I can trap fluids. And when I do, I lost access to them and have to go with my enhanced oil recovery methods. I have to chase it with all kinds of different fluids, from water flood, which is the simplest, to foam flooding and so forth. Okay? So in any event, this is how visualization is actually important. And this is basically all of the steps broken down that I put into that movie. So you can see actually how many I put together. Every line is one of those frames, really. It's just that I filled it with that red color so it looks more realistic. A lot of movies nowadays will simulate fluids and fluid movements, right? That is quasi-realistic. So they're doing a little shortcuts, but they're still capturing the main behavior, which is why it looks real. So a lot of animation is happening because we actually know the equations. There's engineering behind it. We know the equations that guide those movies. But in engineering, we use them to actually validate our predictions. Visualization is very important in that process. And I'm just going to show you one more that is kind of more advanced. So I'm going to stick with fractures. And there's also coupling fluid and particulate movement. So a lot of fluids that we use in engineering are complex fluids. Can you name one? Ones that we inject? Drilling fluid? Drilling fluid. We created. It's a bunch of water, sand, and all kinds of other stuff that keeps that sand suspended. Okay? And the reason why we have to have heavier fluid than the water, because that heavier fluid is supposed to bring out our rock that has been ground up, okay? And just water will not do it. So we need drilling fluid. And then the second one is the fluid with propellant. So if I open a fracture with hydraulic fracturing, I want it open so fluids can move through, otherwise it's going to close back down. And for that, I got to literally prop it with propellant, and those are particulates. So you have a fluid plus particulates, so you have solids, pieces of solids moving along with the fluid, so that takes coupling of how the two behave. So that equation, so here is a fracture, and this fracture is sort of an image. I spoke about X-ray vision before. Well, X-ray vision gives us ability to capture three-dimensional geometry and move through it. So this is one example fracture that you can see in a sandstone. And I'm going to show you, I'm going to just move through. There's a lot of equations, but I'm going to move through to the visualization of how this propellant moves in that fracture. Okay. So this is actually looking top down. When you see contact, that's actually where fracture surfaces are in contact. So those are super tight spots, but fluid can move through the rest. Okay? And you can actually now see particles moving in. What we want from that procedure is that they are kind of spread out everywhere so they keep the fracture properly open. If they drop out, if this is actually a vertical fracture, a lot of them might drop out on the bottom. I don't want that. Okay? It's not going to be properly open. So we also have to design rheology or viscosity of the fluid. Typically, the more viscous fluid, the better. But that's not just it, because more viscous is harder to pump. So there is an optimization there between how well can I pump versus how well can I actually prop my fractures open. And the simulation is trying to basically optimize that. Okay? But it's important for me to visualize to actually just see what's going on. So we're going to stop that. Everybody had a cookie? Are there more cookies? Pass them around. And any questions about what I described? Going to play the movie once again? So,
It says it took 100 hours to bring out 48
thank you. This is on a small scale and it's not easy.
Well, why did it take so long?
Because solving a very nonlinear equation, Navier-Stokes describes fluid really well, and it's as ugly as it gets. Because it actually describes anything from like ocean waves, with the wind as a boundary condition, to this movement. Okay? Here, I not only have, I'm tracking every particle separately and deciding who is it colliding with, how is it moving as a response to that. But that's what's intense here. So it's very intense, and I take 48 computers like yours at the same time working together. So parallel simulation will chop any domain, and this is really not just this problem, but any other. If I have a large reservoir, okay, I'm going to chop it up and give each computer, and we have about 48 here, each computer give a little chunk. This one, this one, this one, right? And whatever particles that part sees. And then they will compute something for a moment, and then exchange information. So, because as particle is going to exit this chunk, this one has to know and receive it. Right? So you compute a little, compare nodes, move on. Compute a little, compare nodes, move on. So there's some information, some time that's spent by comparing nodes. But if I don't do that, one computer cannot memory-wise handle this entire domain, even if I had all the time in the world. Right? So essentially, if I had the memory, then maybe it wouldn't take, so this is 48 processor, 100 hours, so it's 4800 hours to get this.
How much memory would that require?
So each of these memory, I should actually look that up. Each of these processors is like a better workstation. So each of them probably has about 16 gigabytes of memory. But it's also just time taken. So there's both how long it's going to take and how much memory do I need? Okay. All right. Now, beyond research, so you're welcome to stop by, talk to me about what I do for research. You're welcome to just stop by and talk to me. Okay? So if you need to talk something, I'm twice as old as you are. Okay? So I've been around for a little longer. I've been through all of the student things. I've been in school for a long time. So I might have some insight. And your parents or friends or whatever might be far away and hard to talk to. So feel free to knock on my door. I readily offer advice, unsolicited or not. If you want my opinion on something, feel free to stop by. Again, because it might be harder to solicit that advice from somebody else older that you know around here. And I have no stake. So your parents, grandmothers, grandparents, aunts, and uncles that have these plans for you, all I want for you is to successfully finish school. I hope that that's what you want as well. Beyond that, I have no horse in the race, okay? So I can give you sort of a look, an independent look on whatever problem you might have. So please feel free to talk to me about Python, about my research, about whatever else is going on in your life. Because again, and that goes for most of the faculty around, we've been around the block, okay? So we actually, even though we don't share those often and don't necessarily impose, we have certain, and you can take those opinions and do whatever you want with them, okay? They're just that, but they might be helpful, okay? All right, excellent. So I think we have about, if there are no other questions. Any more questions? No? There are more cookies. Pass them around, finish them off. It is Friday, we need some extra cookies. And I am going to go back for at least 10 minutes to our new topic. So, I presented 3D visualization only one example, but there is multiple, there's this entire file of different visualizations that I mentioned on the slides, but this file in Python, Jupyter Notebook is posted for you online, so you can look up how to do different other visualizations. We're going to keep going in terms of data and storing data and talking to our computer, communicating with our computer. And we have to learn. So far, I created this X, Y's, and then I plotted them. So I created my own data on the fly in Python. Most often, that's not going to be the case in your professional life. Data will come as a set of measurements from the field, from the lab, from wherever, from literature. Okay? So you need to figure out how to read that data in, do something with it, plot it, understand it, and then make decisions based on that data. So that is basically what you will do in your professional life. So we need to figure out how to get input, and also, after you're done with whatever analysis you're doing, you need to be able to communicate both sort of a pretty result, which is this visualization, okay, that provides certain understanding about the reservoir you're talking about, and the actual data that goes along that you might have produced. So you have to store that in a way that your colleague can read. For that, we will use files. But files have formats. And unless you understand what are you writing out, and the person you're talking to understands what are they reading, there will be no communication. Just like in human communication and language, if I start speaking Croatian here, nobody will understand me. Well, Croatian is a fully developed language, but unless you understand it, good luck, right? so that we have to file format our language, right? So we need to know how to communicate, both speak in a language and then understand what's being spoken. In this case, we have to work with data, and we need to write that data, and then somebody else will read it, and hopefully read it correctly. Okay, so this is our next chart. Okay. So first simplest thing would be getting an input from a user that is not created by a function, but just input. Okay? So you can actually say, hey, I'm going to store the result in string input, or however you want to call it. You can type in input. Actually, that could be it. You could just give it empty brackets. But you can also, since this has to be understandable to humans, you can actually pose a question that you want somebody to answer. So let's give that a shot. I'm going to call that lecture 2.6. So I'm going to open a new Jupyter notebook. New notebook. Okay. So I'm going to say string input. And this is just enter something. Or talk to me. It's like your mother speaking. Talk to me. Uh-huh. Computer now talking. And I'd say hello. And I typed in something, right? That something is supposedly stored. So let's print it. Oh, okay, it got it. So the communication here went well. Whatever it is that I typed in, after being prompted, it did get stored. And type of this, oh, my caps lock, okay. Type is string, so it's text data. So whatever you type in is going to be interpreted as text, not necessarily as numbers. Okay. So we can continue this conversation. I can say, how old are you? "42, thanks for asking." Then it said I'm W age, I am W age. So how do I get this age back? Okay. And then we can work with that. I can actually say you are years old. Let's see how this works. So all I did with print command, you can throw everything and the kitchen sink to print command. It's going to be pretty good at it. So you just divide it, like whatever it is that you want printed, you just keep adding the commas. Oh. There's also another thing that it works. So what's nice about, let's actually see the difference. I'm going to cut copy. Plus also works. But you're going to tell me what the difference is. No space. So plus basically just takes these strings and just puts them together. Doesn't think about it at all. Comma will just give you a space in between and kind of print it a little nicer. Okay? Now, is this 42, is that a number? Can I say age plus 7? How old am I going to be in 8 years? Uh-oh. What happened? It's a string. So what can I do? There are certain common sense things we can do. Change it. How do I change it to an integer? Just say integer of it. And this will work. Oh my, I'm going to be 58 years from now. You'll see Dr. Bauhoff and I drinking in Jose 8 years from now. Commiserating being 50. I think you're 1 year behind me, aren't you? Alright, so 9 years from now. Okay. So, but 50 is a new 30, what can I say? Anyway, so basically there are certain common things. You cannot do that hello, converting it to integer doesn't make sense, but this does. And this is one way we can, so importance here is that I can get the data from the user and I can work with it, interpret it, put it back. Okay? Right now, just through the screen. Next time, we'll learn about files.